This boy has lived here on a wheat farm in the state of Washington all his life. So he's accustomed to seeing rocks as big as a house. These huge boulders, called haystack rocks by the farmers, have been here longer than anyone can remember. But have they always been here? There are none of these boulders out on the flat plain. They occur only on the rougher, hilly parts of the land. What's underneath the boulders? To find out, let's scrape off some of the topsoil. Beneath the sandy soil, the hills are composed mostly of gravel and small boulders loosely mixed together. Still farther down are flat layers of hardened lava. Evidently, the gravel and rocks were piled on top of these lava flows, and the huge boulders were deposited along with the gravel and rocks. What could have dumped all this material here? From the air, we can see that the rock and gravel hills cover many square miles, but end abruptly. Where did all this material come from? And how did it get here? We'll come back to these questions later. This is the Missouri River near Bismarck, North Dakota. Only a few miles away is this deserted river channel. The channel is wide enough to hold as much water as flows in the Missouri River, but only a small creek is wandering through it. It seems very unlikely that a creek this small could ever have carved out a channel this wide. What then is a channel wide enough to hold a river doing here where even in the wettest season there is only enough water flowing to make a small creek? Sometime in the past there must have been enough water flowing here to cut the wide channel. Where could that water have come from? This rock is in Yosemite National Park in California. Like other rocks, most of its surface is rough. But in some places, the same rock has a surface that seems to have been scraped and polished. The polishing must have been done a long time ago, because some patches of the polish have had time to weather away. Most of the polished rock is also grooved and scratched, as though something had been dragged over it. Grooved, scratched, and polished rock is also found in many other places. In the Rocky Mountains, around the Great Lakes, in New England, and in Central Park in New York. At each place where such grooves or scratches are found, they are always roughly parallel and tend to run in a north-south direction. It is unlikely that a river carrying sand and gravel could have made grooves, scratches, and polish of the kind we have seen, because the best examples are usually found on the tops of mounds of solid rock, just where a river would not flow. How then were markings like these made? This is a canyon cut by a stream into a mountain range in Utah. Like most mountain canyons, it has the shape of a V. A few miles away in the same mountains, and carved into the same kind of rock, is a valley that is not V-shaped, but has a wider, more rounded U-shape. Such U-shaped valleys are found most commonly in the highest parts of mountains. Up here, streams are small. They're just getting started and have little cutting power. So it is unlikely that a stream could have cut a wide, rounded valley like this one. How then can we account for these valleys? If streams couldn't have cut them, what did? This is a copper mine in Upper Michigan. It is located in the only region in North America where large quantities of copper have been found in the rock as metal. The mine is located here, near Lake Superior. Hundreds of miles south of the mine, surprising discoveries have been made. Stray pieces of metallic copper, coated green from exposure, have been found lying on the ground or in the soil at many different locations. Here are some of these locations. The drainage system for this area looks like this. If the chunks of copper came from the area around the mine, they must have moved to these locations across most of the streams and rivers. So it seems unlikely that rivers could have carried the copper pieces this far. And even if rivers could have moved them, it is still less likely that they could have left the copper chunks between river courses on high ground. How then did they get there? Stray pieces of copper, U-shaped mountain valleys, scratched and polished rock, abandoned river channels, haystack boulders, all are problems and puzzles that cannot be answered in terms of any geologic process at work at these places today. But there is one geologic process that might answer all of these questions. This is the continent of Antarctica. Below is glacial ice, in some places over 2 miles thick. Glaciers form in places where the snow accumulates faster than it can evaporate or melt away. In such places, the snow continues to pile up year after year. The deeper the snow gets, the greater is the pressure on the snow underneath. Gradually, the weight of many tons of overlying snow causes the buried snow to turn into ice. So most of a glacier is made of ice. This glacier is in Canada. It is called a valley glacier. This is the edge of the glacier. It is covered with rocks that have fallen onto the ice from the steep walls of the valley. Looking down the glacier, we can see where a smaller glacier joins the main one. Where the two glaciers meet, the rocks along their edges join to form a dark stripe down the ice. This must mean that the glaciers and the rocks on them are moving down the valley. In the summer of 1962, many small markers were placed on the surface of this Canadian glacier. To show the locations of the markers, we have placed some large cloth targets in the positions where the markers were originally set. A square target on the far side of the valley shows the place which was used as a fixed reference point to mark the end of the straight line. For 2 years, the markers were left undisturbed on the glacier. At the end of 2 years, each marker was found. To show where they were found, we'll use targets again. Now we can see what happened. The glacier moved about 200 feet down the valley. The curve in the line shows that the glacier moved faster near the center. Although the glacier moved too slowly to be seen by watching it, the displaced targets prove that it did move. This is the Blue Glacier in the state of Washington. The glacier doesn't seem to be moving, but is it? During the course of one summer, scientists photographed a small part of this glacier every day. A camera locked into position on bedrock took one photograph at noon on each day. This is how the glacier appeared on the day the first picture was taken. Now watch what happens when all the pictures are projected in sequence. This is what the ice looked like 77 days later. Let's watch the ice movement again, this time at a slightly slower speed. The flicker is caused by changing weather conditions. So, although we can't see the movement of glaciers with the naked eye, we can prove that they do move. What effect does a moving river of ice have on the valley it's moving in? As a glacier like this one in Canada moves downhill, the ice picks up rocks, gravel, and sand from the valley floor and drags them along. The weight of the ice above presses down. As a result, the bottom of the glacier acts like a massive sheet of sandpaper. The result is scratched and polished rock in the valley through which the glacier is moving. Wherever you find polished, scratched, or grooved rock like this, you may be fairly certain a glacier once passed over it. This U-shaped valley is in the mountains of central California. The sides of the valley are scratched and polished. Good evidence that moving ice once scraped high along the valley walls. Many such bits of evidence found here prove that a glacier once filled the valley to at least this height. Now we have a clue as to how U-shaped valleys like this one or this one are formed. These small gullies were cut by running water, and they are shaped like V's. Most valleys in mountains are also shaped like V's. The shape of these valleys is determined by the way the sides of the valleys weather away, and the rock debris slides and creeps down to the streams that flow in the bottoms. There the streams carry away the rock debris, and the result is a V-shaped valley. If a glacier were to move down a valley like this one, it might fill the valley a quarter, a half, or even all the way up to the top. So the moving ice would scrape and scour the sides of the valley as well as the bottom. The result is that when a glacier melts, it leaves behind a changed valley. The V-shaped valley is now shaped more like a U. Whenever we find such a U-shaped valley high in the mountains, we can be sure it once had a glacier in it. In this valley, a glacier must have come down just this far and stopped. The lower part of the valley must have been shaped by running water only, because it is V-shaped. Now that we know more about how glacial ice behaves, we have a clue as to how chunks of copper from the region around this mine in Upper Michigan could have been moved to locations in southern Illinois, almost 600 miles from the mine. A huge sheet of ice moving south could have scraped up the chunks of copper and carried them along. When the glacier melted, the copper pieces were left behind. Where a glacier ends, the ice melts and large quantities of water are released. If a huge ice sheet, such as the one now covering Antarctica, were to melt, enormous quantities of water would be released. Where would the water go? This flat land in North Dakota is part of the floor of what once was a huge lake formed at the edge of a melting ice sheet. The lake was fed and drained by channels like this. Wherever we find such deserted channels and lake floors, we can be sure that a melting glacier was not far away. Where a glacier ends, the rocks, gravel, and sand that were carried along by the ice drop to the ground. Year after year, the material accumulates, and the result is a piling up of the loose rock debris into low hills. If a glacier like this were to melt away completely, leaving the hills of rock debris behind, the land would look very much like the place where earlier we found the haystack boulders. Beneath the topsoil, these hills are no more than piles of loose rocks, gravel, and sand of the kind glaciers drop when they melt. The haystack boulders could have been dumped here with ease by a sheet of moving ice along with the other rock debris. And less than a mile away are these scratched and polished rocks. Scratched and polished rocks, hilly land composed of loose gravel and sand, and the haystack boulders make it clear that a sheet of ice once covered part of this plateau, and that the ice sheet came just this far south and stopped. In fact, we can even see one of the channels made by water from the melting ice as it flowed along the edge of the ice sheet. Here are just a few of the places in North America where evidence of glaciation can be seen. Clearly, glacial ice once covered this much of the land and extended an unknown distance out to sea. Today, glacial ice covers only these areas, so it is obvious that the ice melted back at least once. In some places in North America, 1, 2, and sometimes even as many as 4 deposits of glacial clay, sand, and gravel have been found in the same place, heaped on top of each other. These successive deposits show that an ice sheet moved south and then melted back at least 4 times. What could cause an ice sheet to move south, covering millions of square miles, and then to melt and shrink back again repeatedly? Where does the water to make so much ice come from? And when the ice melts, where does it go?